Alrighty, section 7.1b, we're going to talk about multiplying rational expressions and dividing rational expressions. So, in the last video we talked about what exactly a rational expression was. Rational expression is something like these two guys here. It's a fraction containing polynomials, okay? And it's very important to remember that the denominator cannot equal 0. So there are very certain things you have to look for when you are solving for these, right? We haven't gotten quite to there, but it's important to remember the denominator cannot equal 0. Now, when multiplying rational expressions, it's exactly like multiplying fractions, okay? When you multiply a fraction, let's say you have 2/3 times 3/4, right? 2/3 times 3/4. There's route number 1. You multiply across, multiply just straight across. You end up getting numerator of 6/12, right? Then from there, you can reduce. 6 and 12 both can be divided by 6. You end up getting 1/2. Okay, so that's the bare nitty-gritty multiplying fractions. Multiply the numerators, multiply the denominators, then reduce if you can. However, a little cheater mode, if you want to save yourself some time, is to start by reducing. So same problem, 2/3 times 3/4, right? Well, eventually, what I can think about that is I can write it as 2/3 times, or 2 times 3/4, 3 times 4, put them under one fraction, right? And then I notice that I've got some things that cancel. Those two cancel away to equal 1, and 2 and 4 cancel. I get a 1 on the top and a 2 on the bottom. And notice I get a same answer. Okay, so I get 1/2. Either method is perfectly acceptable, except this pink one is going to help us a lot more, save a lot of time when it comes to multiplying rational expressions, okay? So when variables get involved, you want to go the pink route. You want to start canceling stuff first and then multiply it together, okay? So let's just dive in. Let's dive into example 1. Example A. I've got these two rational expressions. I'm going to rewrite them as 5p minus 5 times 3p, or times 3p squared, so I'm going to put some parentheses around it, 3p squared over p times 10p minus 10. Okay, so I've done what I've done in this pink example back up here. I've put them over one giant fraction, right? Because that's all I did. I mean, it's just timesing, right? It's just multiplying. Multiply the tops, multiply the bottoms. Why not do that within one fraction instead of two fractions, okay? That's all I've done. Now, if I look at this carefully, nothing's going to cancel as it is, which is a huge bummer. That's not a cheater method. So I could go ahead and cancel all these out, and then I could reduce it. But reducing second would be much harder. So let's see if we can maybe, quote-unquote, fix some of these. Maybe get them into more of a factored form so that things will actually cancel, right? So let's start with this 5p minus 5. I see a GCF there. That part, so this guy, is going to become 5 times p minus 1, right? So I take out a 5 from both. What's left over is a p minus 1. That's awesome. My other term in that numerator is a 3p squared, right? So that would be a 3 times p squared. And yeah, I didn't really do anything to that one, but it's gonna play out later that you're gonna see it's going to come in handy if you separate those single terms into multiple parts. Alright, I'll do the same thing on the bottom. P. That is about as basic as you can get. There's really nothing to do there. Sorry. I'm not going to put parentheses around that. I'm just going to put times between. Here, 10p minus 10, that's also got a GCF. So let's do 10 on the outside, and we get a p minus 1. Alright. So I've reduced all of these as much as I can, right? I've got 5 times p minus 1 times 3 times p squared, p times 10 times p minus 1. Okay. Alright, well I see something that'll cancel. Since it's all being multiplied, right, I can cancel that p minus 1. The only thing that's been left in the parentheses. P minus 1 cancels with p minus 1 because they are identical, right? They're identical. It's not p plus 1 and p minus 1. But it's p minus 1, p minus 1. That is the same thing as a 1, so they cancel, right? Let's see. I've got 2 p's on the top and 1 single p on the bottom. My exponent rules say I can cancel those to get just 1 leftover p. And then I've got a 5 on the top and a 10 on the bottom. I can cancel those to be left with a 2 on the bottom. And it doesn't look like there's anything else I can do. So after I've finished canceling, I've got a 3, a p, and a 2. Creates my final product of 3p over 2. 3p over 2. And we're done. Now instead, see, notice how that was a lot easier than trying to multiply all this out and then seeing what cancels, right? Because I just have to go backwards and I would have to multiply it out and then factor it in order to see what canceled. We saw that in the last video. In order to reduce, you need to factor anyways. So never, never, never go the blue route, okay? Always go the pink route. Always try and factor, factor, factor. Take GCFs out to get rid of other factors, right? And you'll get down to something nice and easy. Let's try it again. P minus 4 times 3 over 5p minus 20. Now remember, any whole polynomial, right, is the same thing as that over 1. Same thing goes for numbers. If you had 26, that's the same thing as 26 over 1. So I do still have a rational times a rational. All of the, I guess the best way to call them is integer polynomials, question mark, right? That's not really what they are, but that's how you can see them. All the whole number, quote-unquote, polynomials are the same thing as a rational, just over 1. So I can rewrite this way. And therefore, I get, let's do it in pink, p minus 4 times 3 over 1 times 5p minus 20. Cool. Now it's much easier to see that I can start reducing stuff. So let's go top. P minus 4 and 3. Actually, not much to do there. So that would be p minus 4 and 3, right? Because p minus 4 don't have any GCFs, right? It's not a special case. It's not squared. So that's pretty much as basic as you can get. And then 3 is just a 3. That's even more basic. So let's try the second bottom. Times 1 is not really going to do anything, so I can just leave it off. But the 5p minus 20, that's got a common factor, right? And I really should have put that in parentheses, so my apologies. 5p minus 20 is a factor of 5, so I can go ahead and take that out. And what's left over is a p minus 4. So I can factor out the p minus 4. Now I can see that p minus 4 cancels with p minus 4, right? Couldn't do that before. Couldn't just cancel p and 5p because they're both in binomials. They've got those parentheses around them. But instead, now that they're both separate, now that they're identical, even though they've got parentheses still, they're identical, I can cancel them. I'm left with 3/5 as my multiplication. Sweet. Easy peasy. Well, let's try another one. Alright, I got some trinomials this time. So I've got k squared plus 2k minus 15 over k squared minus 4k plus 3, that's my first rational, times k squared minus k over k squared plus k minus 20. There's a lot of k squareds going on here, so I can see your temptation in wanting to cancel. But remember, we can't cancel things like this. If there's a plus or a minus, that's one big thing. You have to take it all or nothing, right? You gotta take it all or nothing. So let's start by factoring each of these. Let's do the top first actually no, I take that back. Let's not start by factoring. Let's put them all over one big fraction like we've been doing. So I've got, no, actually I take that back. We'll build a fraction in a sec. Let's factor first because that's going to make it look prettier. We'll start with k squared plus 2k minus 15. Plus 2k minus 15. Let's see. What would that factor to? Let's see. Two things that multiply to negative 15, add to 2. That's going to be 5 and 3. In order to get positive, 5 is going to have to be positive. So we have k squared plus 5k minus 3k minus 15. Factor by grouping. We end up with k plus 5 and k minus 3. Again, if that's a little ambiguous to you as to how that happened, you need to go back to the 6.2 video and watch that over again. So now I'm going to start building my huge, long, large fraction. And my first numerator actually factored down into k plus 5 and k plus 3. Alright, let's do the second one. I'm going to do the bottom now. So I'm going to do k squared minus 4k plus 3. So here's k squared minus 4k plus 3. That would be this guy right here. All right, two numbers that multiply to 3 and add to negative 4, that'd be negative 3 and negative 1. So it's going to factor into k squared minus 3k minus k plus 3, right? So I took the 4 and I broke it into negative 3 and negative 1. End up with k minus 3 and k minus 1. Okay, so that's the first part of my denominator. K minus 3 and k minus 1. Let's keep going. Let's do the other one. So numerator, k squared minus k. Ooh, this one looks easier because it's not a trinomial, right? Yes, I do still have a k, but it's not a trinomial, so I can just start with GCF. I take out a k, I'm left with a k minus 1. Oh, that was easy. So I have times k minus 1. And then last but not least, let's do the last one. K squared plus k minus 20. K squared plus k minus 20. Let's see, two numbers that would multiply to negative 20 and add to positive 1. I see 5 and 4 sound good. Those are pretty close to 1. How would I get that to be equal positive 1? It'd have to be a positive 5. So k squared plus 5k minus 4k minus 20, right? Factor by grouping, you end up with k plus 5 and k minus 4. And so I've got k plus 5, k minus 4. Okay, so I finally factored all these guys. Now I can see what cancels, right? Got lots of k plus k minus going on here. So let's see what cancels. Well, I've got a k plus 5 and a k plus 5. Here we go with canceling. I have, let's see, do I have any k plus 3s in the denominator? Not so much. Do I have any k's in the denominator? No. Do I have any k? Ooh, I have a k minus 1. That'll cancel. Ooh. Fabulous. Now notice I had a k plus 3 and a k minus 3, but those are not identical, so those do not cancel. And I'm left with k minus 3 over, sorry, k plus 3 is in the numerator. K plus 3, that's what was left over here. Oh, and a k. So times k over k minus 3, k minus 4. And that is my final answer. That is as reduced as I can go, right? That is as reduced as I could go. Some people are probably asking, do we need to multiply back out? You are welcome to. That's another way to represent it. However, it is not necessary. Okay, it's definitely not necessary. All of that work to get it undone, I feel like you shouldn't have to put it back together. If you want to, fine. If you see it like that in an answer, you should be able to tell the difference, right? But this would be fine as a final answer for me. All right, let's do one more multiplication. I've got x squared plus 2x over x plus 1 times x squared minus 1 over x cubed plus x squared. So a lot of x's going on here, but same thing. I'm just going to start by breaking all 4 down. Right, just break all 4 down. So I've got x squared plus 2x. Got a GCF of x here. I get x plus 2. Right, set up that new fraction. You know what, before I do that, I'm going to cut off the problem here so we can tell where we are working. Okay, cool. So then here, got x and x plus 2. It's the first part of my fraction. Alright, so check on that one. That one was pretty easy. X plus 1, that is as reduced as you can get. So we'll just call it an x plus 1. Since I'm putting things under one fraction, though, I'll put it in parentheses, just in case. Then we've got the second numerator. That's x squared minus 1. Alright, so x squared minus 1. I see a special case, the difference of two squares, right? One is a squared. X squared is obviously a squared, and they're being subtracted. So this factors into x plus 1, x minus 1. Again, if that's ambiguous for you, you need to go back and see 6.3. Okay, you need to go back right now. So pause this video, wherever it is, go over to 6.3 and watch that. Alright, so up on here we get x plus 1 and x minus 1. And then last but not least, we have x cubed plus x squared. There's brown. X cubed plus x squared. Just because it's a cube doesn't mean anything's different, right? We've got a factor of x squared here, and x plus 1. And that's as pretty much as I can factor down. So x squared and x plus 1. Alright, now we go with canceling. I have an x plus 1 here and an x plus 1 there. Be very careful. Just because I have two x plus 1s on the bottom doesn't mean I get to cancel both, right? I can only cancel with one. It's one of each, right? If I had two x plus 1s on the top, that'd be awesome because I could cancel both of them. But I've only got one on the top, so I can only cancel with one on the bottom. Same story goes for the x's here. I've got one on the top and two on the bottom, so I'm left with one on the bottom. X plus 2, nothing on the bottom to cancel. X minus 1, nothing on the bottom to cancel. So I'm left with x plus 2, x minus 1 over x plus 1. And again, if you want to multiply this all back out, you're more than welcome to. However, I think it is more beautiful like this, and I can see where your train of logic lies, so if you wanted to leave it here, I would be okay with that. Alrighty. Hopefully this is starting to make sense. Notice it's a lot of just factoring and canceling, factoring and canceling. Multiplication is so very, very similar to reducing that's why it's in the same section. Like, it's almost virtually the same thing. Let's try dividing now. Before we hit dividing, though, let's talk about a reciprocal. Reciprocals are the same for fractions and rational functions, okay? Reciprocals just mean flip the fraction. Flip the fraction. Basically, you switch the place of the numerator and the denominator. So if you had a fraction of negative 3/4, then the reciprocal, well, we'll come back to that one in a sec. Let's do 27 over 32. The reciprocal would be 32 over 27, right? So you just flip it over. If you had 2/3, it'd be 3/2. If you had 1/3, become 3 over 1, or 3, right? And then if you had a reciprocal of 4, well, that's the same thing as 4 over 1 becomes 1/4, right? So the reciprocal is going to be flip the fraction. And I actually should draw arrows. However, with the negative, the only other thing you have to remember is when, hold on, there we go, is when you're trying to find the reciprocal here, by all means, you may flip, right? 4 over negative 3, but you don't really want to leave a negative in the bottom. So just pull it to the top, or even better, the outside, you get negative 4/3. Okay, so reciprocals don't change the sign. That's opposite. Reciprocals just change the fraction. What about mixed numbers? Well, in mixed numbers, first change it to an improper fraction, a fraction that is, bigger on the top than it is on the bottom. In order to do that, you can think of this as, okay, I have 4/9, right? I also have 3 whole things, which would be 27/9, right? 27 divided by 9 would be 3. Add them together, you get 31 over 9. So that's how you change it into an improper fraction. After that, reciprocal is pretty easy, 9 over 31. Just flip it over. Okay. So if you have a mixed number, change it to a improper fraction first. You can actually find them for decimals as well. Just change it to a fraction first, right? So 4.2 is the same thing as 42 out of 100. I like to go with out of 100 when it comes to decimals because I just have to move the decimal place over until I get a whole number. So if I've got 4.2, that's 4.2 out of 10. That doesn't really help me because it's still a decimal. But 42 hundredths would be the same thing. So move the decimal place over 1. 42 out of 100. No, it's not. 420 out of 100, sorry. 420 out of 100, move it twice. Move it twice. Take back what I just said. Let me show you. So this is the same thing as that over 1, right? In order to move it once over, you add 1 0. So 42 out of 10. And it would be, if you moved it over one more time, pardon me, it'd be 400. Or 420 out of 420. 420 out of 10, but we don't need to go that high. My apologies on that. So 42 out of 10, not 42 out of 100. Then we can find the reciprocal quite easily by flipping the fraction. 10 out of 42. That's the reciprocal. Alright, so that was a little refresher course on reciprocals for numbers. Let's try with a few rationals now. The rationals are virtually the same thing. It's exactly the same thing, right? It's important to remember that if we end up with something on the bottom that has a variable, if our denominator has a variable, that variable cannot equal 0. But since these are just expressions right now, we don't have to worry about that. They're just expressions. So let's just flip them. So the reciprocal of 3x over 4, 4 over 3x. Easy. The reciprocal of 4x squared over 3y, that would become 3y over 4x squared. It's important to note that I am not writing equal signs in between these two, right? Because they are not the same thing. A reciprocal is not equal to its original, okay? Original is not equal to its reciprocal. They are two separate fractions. But when I multiply them, notice that those two will cancel and those two will cancel, and I'm left with 1. That's what a reciprocal does. A reciprocal cancels out the top and bottom. That's why we flip it. So this reciprocal was 3y over 4x squared. Alright, let's try this one. M squared over 9m over 2. I'm sorry, m squared minus 9m over 2. Reciprocal of that would be 2 over m squared minus 9m. And then finally, the reciprocal for this one would take the numerator and stick it in the denominator, and take the denominator and stick it in the numerator. Do I have to simplify? No, they didn't ask me to. Chances are, they just are. Honestly, when we use this in division, it's just to help us cancel, like I did in this last problem. So we don't need to simplify it. You will probably in division, but here, you don't need to simplify. Alright, that was reciprocals for rationals. Let's actually use it to divide now. Okay. So, dividing fractions. Remember, in order to divide a fraction, that's the same thing as multiplying by the reciprocal, okay? So if I'm dividing this 3/4 divided by 5 over 6, well, what that essentially says is 3/4 divided by 5 divided by 6, right? That's a lot of divided. So it ends up canceling out and you get a multiplication. The same way as when you multiply by 2 negatives, you're multiplying by a positive, right? So same thing, you're canceling out this division. So let's change this. We'll keep the first one the same. Instead, we'll times it by the reciprocal, 6/5 instead of 5/6. And when we do that, we can kind of play cheater. This would be, okay, so I can divide those both by 2. I get 3 and 2. 3 times 3 is 9 over 2 times 5, which would be 10. That would be my final answer. 18 over 9. 18 over 20 would also reduce down to 9 over 10. Good. Alright, that's dividing fractions. Let's do it again. So I don't want to divide, I actually want to multiply, but I'll multiply by the reciprocal. So I'll keep the first one the same, and I'll change the second one to its reciprocal. 2 over 9 instead of 9 over 2. Now remember, division is like subtraction. It does matter what order you have, right? And you can see why. If I wrote those in a different order, then I would be flipping a different fraction. So it's important to keep the fractions in order, right? It's important to keep the numbers in order. 72 divided by 9 is not the same thing as 9 divided by 72, right? So make sure you know which one you're actually going to switch, right? It's always going to be the second one. Alright, then we can't really do anything cheater-wise, so let's just go ahead and multiply across, multiply 16 over 27, and yep, that does not reduce, so that's our final answer. Alrighty, dividing fractions. Pretty easy. Let's throw in a few variables, right? Let's change it to rational expressions. No big deal though, right? It's the same thing. It's just fractions with variables. So let's see if we can do it here. Same thing. Keep the first one the same. And multiply by the reciprocal of the second one. My z's are horrible, so I'm going to rewrite that. So 2z over 9 times 8 over 5z squared. Okay, cool. None of these are even binomials, so this is still pretty easy, right? 9 and 8, nothing cancels. 5 and 2, nothing cancels. But I do have a z and a z squared. And that will give me 1z down here. So I end up with 16, 2 times 8, over 5 times 9, which is 45, and a z. There's my final answer. Easy peasy, lemon squeezy. Okay, cool. Now let's try one with binomials. First, I'm going to change it to a multiplication problem. So first, I'm going to continue like nothing has changed. I've got 8k minus 16 over 3k, leave that one the same, times, now I'll use the reciprocal, 4k squared over 3k minus 6. So starting with the reciprocal, that changes it from a division problem into a multiplication problem, right? Now we've already done this, right? We've done multiplication problems. I can't quite multiply this way. I mean, I could. You definitely stick them all over one fraction, but not a lot's going to cancel as I have here, right? So first I need to take a look at each numerator, each denominator, and I need to factor it down. So let's factor this first one down. 8k minus 16. 8k minus 16. All right. I'm going to rewrite this just a little prettier. Okay. I see a GCF there, so I end up with 8 on the outside and k minus 2. All right, cool. So 8 times k minus 2. The second one, 4k squared. Really, that doesn't factor into anything much more, so I just get 4k squared. And I'll write it in a different color. 4k squared. The one on the bottom, again, doesn't really factor into much. 3k is about as simple as you can get, right? You can have a 3 and you can have a k. They're kind of like unlike terms. It's even one term. So, and then lastly, we've got, let's not do pink, let's do purple. 3k minus 6. What can factor out? A 3. I'm left with a k minus 2. Alright, so 3 and k minus 2. Alright, now everything is nice and easily factored out, right? Everything's in lowest terms, so I see that there's a k minus 2 that will cancel. And I see there's a k here that will cancel, leaving me with 1 extra k on the top. 3 and, let's see, 3 and 4 and 8 really don't have anything in common. So I end up with 8 times 4, which is 32, and an extra k, over 3 times 3, which is 9. That is the division of those two rational expressions, pardon. Okay, so once again, change it to multiplication, reduce, cancel, you're done. It's like 4 steps. You're good. Let's try. Alrighty, let's try this one. So, yes, it looks larger. Yes, it looks more intimidating, but it's the same steps, right? It's the same exact steps. And I'm just going to go one by one. I'm not going to try and freak myself out. So I'm just going to start by switching it to a multiplication problem, just like we did in the last problem. The first rational expression stays the same. First numerator was 5m squared plus, let's see, 17m minus 12. And that is over 3m squared. 3m squared plus 7m minus 20. Okay? I have done nothing to that problem. Now I'll take the second one. I'm going to change it to a multiplication and use the reciprocal. So now the new numerator is going to be this polynomial. 15m squared minus 34m. Oops. Let's write an actual 4 there. Plus 15. And the new denominator is going to be this guy. 5m squared, so over. 5m squared plus 2m minus 3. Yep. Okay, so all I've done is switch these two polynomials here at the end. Now, just like in our last multiplication problems, I'm going to take each one of those and I'm going to factor them, right? So I'm going to take each one of those individually. If I try to do all 4 of them at the same time, of course my mind's going to explode. So I'll take them one at a time. Here is the first numerator that I see in the problem, right? Nope, minus 12, sorry. Alright, now I'm going to pretend the rest of this problem doesn't exist. I'm going to focus solely on this guy right here. So, 5m squared plus 17m plus 12. Let's see, a times c, 5 times negative 12 is going to be negative 60. Two numbers that multiply to negative 60 and add to positive 17. Let's see. Can't be 5 and 12 because if I add those, that's going to be, one of them has to be negative. Can't get to negative 7, I can't get to 17 with one of them being negative. 20 and 3 sound pretty good for 60, and I think the 20 is going to have to be the positive one. So 20 and negative 3. 20 and negative 3. Alright, when I do that, I'll split this guy into 5m plus 20m minus 3m minus 12. And I'll factor by grouping. So I split 17 into 20 and minus 3, right? Because 17 is 20 minus 3. Now I can take out in this first one, I've got a 5m in common. So 5m. What's left over is m plus 4. In this second one, it looks like I've got a negative 3 in common. I've got m plus 4. And lastly, I have 5m minus 3 times m plus 4. Okay, so my first numerator now reduces to 5m minus 3 and m plus 4. Alright, that'll be the first part of my big, huge fraction that I will deal with at the end. Okay, I'm done with that. I am no longer concerning myself with the first polynomial. I'm going one polynomial at a time. One polynomial at a time. So next, I think I'll tackle this bottom denominator polynomial, this one right here. Actually, let's do this one. Let's call it this one. I'll put it in red. So I have 3m squared plus 7m minus 20. Alright, 3 times negative 20 is also negative 60. And let's see, two things that multiply together to give me that, and add to 7. I think 5 and 12 would give me 60, and negative 5. Okay, so negative 5 and negative 12. So 3m squared minus 5m plus 12m minus 20. Alright, and then because that splits 12 minus 5 would be 7. So I can split it that way. Factor by grouping. I get, let's see, those guys just have an m in common. 3m minus 5 is left over, because that's a squared. Here, 12 and 20, they both have a 4 in common. So plus positive 4, and I get I get 3m minus 5 left over. Okay, last but not least, it's m plus 4 and 3m minus 5. Take out the 3m minus 5, I'm left with m plus 4 and 3m minus 5. So that was the first denominator. Okay, I'm just going to erase that real fast so that I can fit it in there. So m plus 4 and 3m minus 5. Alright, 2 down, 2 to go. Cool. Well, let's take a look at the 15. Let's do that one in blue. 15m squared minus 34m plus 15. Let's see, 15 times 15 is 225. Two things that multiply to 225 and add to negative 34. That one is a little trickier because it's a little bigger. Unfortunately, there's no GCF, so I can't take it out. But let's see, 225. Let's see, so that sounds like 225 sounds an awful lot like it could be divided by 5. 5 and 45? No, those don't add to 34. Let's try 25. 25 and 9? Ooh, if they're both negative, that would work. So 25 and 9. Negative and negative. They give me my negative 34. Alrighty. Let's go ahead and do that. So 15m squared minus 25m minus 9m plus 15. Factor by grouping. Sorry. And let's see, the first one has a 5 in common and an m in common, so 5m. Leaves me 3m minus 5. This second one, 9m plus 15, looks like they have minus 9m plus 15. Looks like they have a minus 3 in common. I get 3m minus 5. And so it looks like my final factored form is 3m minus 5 and m minus 3. Again, if that was a little ambiguous to you, you need to go back to 6.2. Alright, and that was the second numerator. So the 3m minus 5 and 5m minus 3. do the same thing with the last one. We have 5m squared plus 2m minus 3. I'm going to try and write it real small down here in green. 5m squared plus 2m minus 3. Alright, multiplies to negative 15, right? A times c adds to 2. Well, that would be 5 and negative 3. So 5m squared plus 5m minus 3m minus 3. Factor by grouping. Okay, these guys have a 5m in common. Left over with an m plus 1. These guys have a negative 3 in common. Left over m plus 1. So my factored form is m plus 1 and 5m minus 3. Alright, so down here on the bottom it'd be m plus 1 and 5m minus 3. 1, 2, 3, 4 polynomials completely factored. Cool. Yes, it took some time, but it was a lot of the same thing over and over and over again. Next we go with canceling. Let's go with canceling. So we'll do it in orange. 5m minus 3. Do I have any of those on the bottom? I do. I can cancel that one with that one. Awesome. M plus 4. Do I have any of those on the bottom? I do right there. Oops. M plus 4. 3m minus 5. 3m minus 5. Check, check. And 3m minus 1, or 5m minus 3? Nope, the only thing I left is 3m minus 1. So my final final multiplication is just going to be, let's do it in purple so we can see it. And let's put it, I'll just erase this blue part for a sec. Okay, so our final factor, our final multiplication, our final product is going to be this guy over this guy, which is 5m minus 3 over m plus 1. Nice and easy, right? Same 4 steps, right? So switch to a multiplication problem, simplify each of your numerators and denominators, cancel, find out what you have for a product. Very long problem, not complicated problem. Just long, that's all. All you need to do is drink a Red Bull and you'll be able to do it. Alright, one more. Let's try one more. I have k squared minus 4 over 3k squared divided by 2 minus k over 11k. Much smaller things should go a little faster. But again, doesn't matter if they're big. Big numbers are just big. That's really their only thing. They're really not that intimidating. They don't have many muscles. Think of them as more like Jack Black, not really The Rock, okay? Just because he's large doesn't mean he's going to hurt you. It's Jack Black. Like, come on. So, think of these more as Jack Blacks instead of Dwayne Johnson. Alright, cool. So let's do our same 5 steps. Let's go ahead and flip that so we still have the same k squared minus 4 over 3k squared. Now this is times the reciprocal, 11k over 2 minus k. Alright, now I'll take each one and I can reduce it. So k minus 2, k squared minus 4 is a special case. It's going to be the special case of k plus 2, k minus 2. Again, if you don't remember that, you need to go back to 6.3. 11k is pretty much as simplified as you can get. So 11k. 3k squared, again, about as simplified as you can get. 2 minus k is fine as it is. It's definitely reduced. But since I'm noticing this k minus 2 up here, I think I'm going to pull out a negative 1 and get k minus 2. Right? Remember that from a few times back up in reducing, right? Pulling it out. That way I can see that these two guys match. So k minus 2 cancels with a k minus 2. I don't have any k plus 2s. I have a k here. Oops, sorry. That I can cancel with this k, and I'm left with one more k. And then 11 and 3 and negative 1, no, they don't really cancel all that much. Alright, so I've got an 11 and a k plus 2. I've got a negative 1 and a 3 and a k. And then if we reduce this a little bit, we can pull that negative part out just in general. We get 11 k plus 2 over 3k. And that's our final answer. Awesome. Alright, that was multiplying and dividing. I hope it answered your questions. Otherwise, feel free to email me. I will see you in 7.2.